going to get started now. So today's recitation is the long-awaited Malloc Recitation. I'm sure this is what you are here in the course for. This is what you've been waiting for the whole time, right? Malloc Lab. So Malloc Lab is out. It came out on Tuesday. So hopefully some of you have looked at it, maybe even started it. If you haven't, you should do that soon. It might seem like it's not due for a while, but this is a big lab, so you want to get started on it as soon as possible. And after the stuff we go over today, you'll be well prepared to get working on it. So we're going to talk about a couple different things today. We're going to talk about macros and inline functions and how to use them and the differences between them. Both of those will probably show up in your Malloc Lab somewhere. Certainly you'll have at least one of the two. We'll talk about pointers a little bit, pointer arithmetic, some of the rules for that, because you'll be doing a lot of that in your Malloc Lab. And then we'll talk about the high-level design of Malloc and what you want to be doing, and sort of show off a couple tips and tricks that will hopefully make your lives easier when you're actually implementing it. So macros and inline functions. So macros, we talked about these earlier in the year. I think we discussed them way back, like sometime around maybe before Cache Lab, and then we talked about them at the C review if you went to that. Macros are a mechanism in C where before the program gets compiled, you can do find and replace with certain patterns. So you can define a constant. For instance, you can say num entries is defined as 100, and then before a program compiles, it'll go through and it'll replace every time where it sees num entries with the number 100. But you can also use these to define simple operations. So you can give these, parameters, and essentially it's, you can almost make like a little function with it, but it's not quite the same as a function because it still is find and replace. So you have to be careful with these. For instance, in this one where we just did 2 times x, then if we just put in x plus 1 down at the body where we're actually using it, then x just gets replaced with x plus 1. And now what we see is that we've actually not computed twice of x, but we've done 2 times x plus 1 because the order of operations just happens in whatever it is once you do the find and replace. So you want to always make sure that if you're, anytime you do a macro that's more than just like a constant, you want to always make sure that it's wrapped in parentheses along the outside so that where you use it doesn't sort of rip it apart and pull it into a couple different halves based on the order of operations. So why would we use macros? Macros are faster than function calls. Does anyone have an idea of why macros would be faster than function calls based on the fact that it's just a find and replace? No idea. You all did Bomb Lab. Yeah? Yeah, we've got all these calling conventions for function calls where we have to like move stuff into registers and we have to do a jump, and then we might be playing with the stack pointer, and then when we're done with it we have to like undo all of that and jump back to where we were before. And if we're just doing something like multiplying by 2, that's a whole lot of work for something that's pretty simple. So the fact that we're just finding and replacing means that we don't have to do all of those calling conventions everywhere it's called, because it's actually never going to call anything. It's just replacing it with the body everywhere where it occurs. And it allows us to update all of those occurrences at once rather than in a way that will compile to something faster, rather than writing it out manually every time. So for Malloc, you would get a lot of use out of macros, potentially for playing around with your stuff like your header information and your payload size and that sort of stuff. You'll be keeping these blocks of information that correspond to the free blocks and the allocated blocks in your program, and each one is going to have some number of bytes attached to it that keep track of relevant information like how big it is and if it's free or not, or whatever else you choose to keep. And macros will be a good way to sort of access that information, because that'll just be a little bit of pointer arithmetic and maybe masking off some bits or whatever. Macros are a great way because you'll be doing it all over the place. You don't want it to be slow function calls. Macros will be a great way to have a unified interface for that. Drawbacks of macros, they're not as expressive as functions. You can't do everything you can do with a function with macros because they don't have a return. Sort of, it replaces with the body. You're not actually returning something. You're not actually given type-checked local variables, so the arguments to a macro, you just replace it with whatever's in there. You can't assert that you can only put an int in there. That would only, the type checking happens after the replacement, and that can be confusing. And also the variables aren't local variables, so if you're doing sort of state updates, if something in there is like a pointer or update state somehow, you might not be able to easily see what's going on. So inline functions are sort of the other thing that you might be using in Malloc Lab in addition to macros, sort of in a similar way. So there's this keyword inline. So if you're defining a function in a file and it's the same file you're going to use it in, you can inline the function. And what it does is at compile time, so the macros were before you compile, you do the replacement. Inline functions at compiler time, what the compiler will go ahead and do is it'll replace the function call with the body of the function code. And then it can get away with not doing the whole stack conventions, calling conventions thing, because it's actually not making a call. So it sort of just expands the call into the actual body of the function everywhere where it's used. So this is still less overhead than a full function call. But what you get is you get sort of the full benefits of having type-checked arguments, and the arguments are local variables within the function and that sort of stuff, which you didn't get in macros. So here's a comparison between the two. Stuff that we've already said. Let's see. Here's an example of unintended side effects in a macro. So say we have a macro that's supposed to just square a number, but we give it x plus plus. Well, then it gets replaced with x plus plus times x plus plus, which means we do the increment twice, which might not be obvious to us when we're using the macro because, well, it doesn't look like it's, it looks like a function call here. You would think that, the x plus plus would only be done once, which is what happens in a function call. Yeah?
What's the syntax for inline functions?
So an inline function is just like a normal function, except when you're declaring the function, if it was like foo, instead of putting int foo, you would put inline int foo. You just add the word inline at the beginning of the function definition.
So why wouldn't you just put inline at most all the functions?
So you don't necessarily want to inline everything in a program because, first of all, if you have a function that's being used a bajillion times and it's a rather large function, then replacing the calls to the function with its code will make your executable huge. That would be a real issue in some programs. Also, so that's one of the issues. Also sometimes, sort of like if maybe you have a situation where you might make a function call, but you don't always make the function call. Maybe you only rarely make the function call. And maybe it's a lot of code. If you inlined it, then you could ruin your locality in the cache of the instructions if all of those instructions are right there. And you're usually not going to go through them, but you're just going to jump past them anyway. Stuff like that. Sort of there's a cost to just replacing it everywhere. And also it also confines you to the same file that you're in, because obviously you can't have a file and a header function inline it if you don't know how it's defined. Stuff like that. So it restricts how you can share functions across files too. So macros can be hard to debug, is the warning there, because all of the error messages you get are going to be error messages on the expanded code rather than the code with the macros in it, because the error messages are generated by the compiler and the macros were replaced before the compiler got to run. So in terms of macros versus inline functions, because they sound pretty similar, so like where do you use which? Macros are good for small tasks, sort of constants, very, very simple operations. So the things that you can't do with macros but can do with inline functions, obviously, you would want to use an inline function for. you might end up, in the end, sort of having cases where you're like, this could be a macro, could be an inline function. I'm not sure which one I want to make it. And at that point, you might want to just try both and see which one is faster. Because it might turn out that, one is faster than the other for whichever particular thing you're doing. And since one of the things you're being graded on is throughput, which is your speed, it's a simple switching back and forth and run the driver on both and see which one turns out better. Okay. So any questions on macros or inline functions? Any other questions? Okay, so pointers. So we've talked about this before. This is a review of some of this stuff because it's all relevant here, so it's good for you to be reminded of it. So first of all, casting. So we talked about casting earlier in the class in terms of, casting integer types. So if we cast from signed to unsigned, or if we're casting a small integer type to a bigger integer type, how that all works. You can also cast between pointer types, and it's the same syntax in terms of writing it down. You write the type that you're casting to in parentheses in front of the expression that you want to cast. But in terms of what it actually does, it's slightly different in the sense that it will always give back the same value. So sort of in the integer casting, like if we were going from a different size types, then we actually give back something with more bytes in it. But in the case of pointers, all pointers are the same size. In 64-bit systems, they're 8 bytes. And so it's just changing the interpretation of what kind of pointer it is. But all pointers can be pointing to whatever, because they're just all 8-byte addresses. So when we do a cast between two pointer types, it always gives back the same value, but it's going to change the behavior that happens when we dereference it or when we do arithmetic on it. And then in terms of casting pointers between the pointer types and the integer types, pointers are just an 8-byte number. So it's similar to casting a long to other types of integer types. It has the same properties. Okay, so it's actually important to note that pointers are really just 8-byte, an 8-byte long integer, essentially. Because in Malloc Lab, you will be writing pointers into locations just as pretty much as numbers that you're manipulating that are a pointer, but since you don't have the ability to actually use malloc to get a pointer, because that's what you're writing, you're doing it a little bit more directly. You're sort of constructing pointers directly by doing arithmetic on them and then giving those to the user. But you have to be careful when you're using pointers as integers, because just going between them carelessly can lead to all sorts of errors. Okay. So pointer arithmetic. So this is something that we've seen before, but it's tricky, so we're going to go over it again. So when you do pointer plus some value, it's not the same thing as if pointer is just an integer in general. So if we had the pointer, I don't know, maybe our pointer is just 0x08, and we do plus 1. If this was an integer, then we'd get 0x09. But in the case of pointers, it actually depends on what type of pointer this is. The result of this depends on what type of pointer this is. Because what happens when you add to a pointer is it adds whatever you're adding times the size of the pointer. So, down here, you can think of this as a couple different ways. You can think of it as this is really doing the value of the pointer plus this times the size. And in terms of assembly, what that looks like is that's a load effective address, where we have the base pointer that it's starting at, and then the thing we're adding times some scaled value is going into pointer 2. So this depends on the type of that pointer. And a thing to note, and this is actually something we had wrong in the slides originally, and one of the other TAs pointed out to me, that pointer arithmetic on void star is undefined. And originally there was an example that I put in the slides that used it, because it turns out that GCC will just treat void stars the same as character pointers. But according to the C standard, it's not necessarily going to be that way. And so GCC could choose to do whatever it wants. And in fact, other compilers will choose to do different things. So you should be careful not to do pointer arithmetic on void star. GCC might not complain, but it's definitely a bad thing to do. It's undefined behavior. Because, the intuition behind that is, you're adding the size of it, the size of the type. So, in a character pointer, you're adding size of character, and an int pointer, size of int. What's size of void? Like, there really is no clear answer of what the size of a void should be. So here's some examples of pointer arithmetic that we can go through. So we just have this sort of dummy address that everything's starting at 1234, 1230. So if that's an int pointer, and then we add 1 to it, what's the address that we get back? What's pointer to? 1234, 1234. Let's see. Yeah, I think there's a typo in this slide. Oh, no. Okay, never mind. I thought I had something else, but no, that's good. That's correct, and is what's in the answers. Don't peek at the other ones. I put them through real quick. Okay, so 1234, 1234. Yep. Because the size of an int is 4, so we just add the size of an int times 1 to the pointer we started with. So that's good. Okay, so now we have a character pointer, 1234, 1230, and we add 1 to it. Now what does it give back? What is the value of pointer 2? Yep, 1234, 1231. So if you look at it, both lines, are just pointer plus 1, pointer plus 1. But the difference between them is the type of pointer. So when pointer is an integer, the plus 1 means 1 times the size of int, which is 4. And when it's a character, it means 1 times the size of character, which is 1. So even though these look very similar, they have different results because the type of pointer is different. So this is 1234, 1231. Here's a trickier one. Same starting address, but now what are we doing? We're casting it to a character pointer and then adding 1 and then casting it to an int pointer. So what do we get back? How about just this inner part, the from here to here? What will that evaluate to?
1234, 1231.
Yep, 1234, 1231. So the cast doesn't change the value of pointer, but it does change the behavior when we do arithmetic or dereferencing on it. So we now have a character pointer that we're adding 1 to. So we've got 1234, 1231, and then we cast it to an int pointer. So what does that do to it? Nothing. Yeah. The cast doesn't change the value of the pointer, just the behavior of dereferencing and arithmetic. So we're left with 1234, 1231 in the end. Okay, so now here we have a character pointer, and then we're going to make a void pointer, pointer 2, by adding 1 to pointer. So what does this do? Any ideas? Well, okay, so what I said was that arithmetic on a void pointer is undefined. But pointer right now is a character pointer, yeah. So the bug in the slides was that originally this was a void pointer here and here, and that would be undefined. But now we're doing arithmetic on the character pointer and then just casting it to a void pointer. It implicitly casts it when the left-hand side has a different type after it does the arithmetic. So then we just get 1234, 1231 again. It's just the same as before. And then over here, well, we're making it an int star, but then it ends up a character pointer anyway. So this doesn't matter. The casts don't change the value of the pointer. Since it becomes a character pointer before we do arithmetic to it, it's 1234, 1231, and then we cast it to a void pointer from there. So we can see the answers here, and they're what we said they were. Okay, here's another slide. These ones are maybe a bit trickier. So now we have an int pointer pointer, 1234, 1230. What happens when we add 1 to that? Plus 8. Yeah, so we get 1234, 1238. Does everyone see why that is? So if it's an int pointer pointer, then what we do when we add 1 is we're adding 1 times the size of int pointer. So that is 8, because we're assuming this is a 64-bit machine. It's the thing down here. So pointers are size 8, so that's what happens. Okay, how about when we have a character pointer and we add 1 to it and then cast it to a short pointer? Same thing, yeah. So adding 1 to a character pointer adds 1 times the size of character pointer, which is 8. So we get 1, 2, 3, 4, 1, 2, 3, 8. And then we cast it to a short pointer, and that doesn't change the value. So it's 1, 2, 3, 4, 1, 2, 3, 8. Okay, how about this guy over here? So let's see. So we've got an int pointer, 1, 2, 3, 4, 1, 2, 3, 0. And we take the address of it and add 1 to that. So what does that give us? Same thing as before?
Yeah, because like it's the address of an address. Like
the address of an address.
it's like an address to a pointer, which is the.
So what is the address of this pointer?
The same thing itself.
Well, is it? So okay, so these are local variables, right? So they're like stack allocated variables. Local variables end up on the stack. So this pointer is being stored in some address on the stack that's been reserved for us by the compiler. And then we take the address of it. So that gives us the stack location where this local variable is being stored. And then we add 1 to that. So who knows what this is? It's probably some address that's somewhere in the stack. But we don't actually know what it is. We can't say that. Because the address of a pointer is not the same as the pointer itself. Okay, and then how about this last one? So this last one is also maybe a bit tricky. So we've got an int pointer, and what do we do to it? We dereference it, add 1, and then cast it to a void pointer. So what does that give us? Yeah, we don't know. What is it doing?
Should it give you the same address?
Give you the same address.
Because it's like you're just adding 1 to the value at that address and then casting that address to.
Adding 1 to the value at that address, but what's the value at this address?
I mean, but that shouldn't matter, right? Because the return type is a void star.
So, okay, well, so it's going to be the value at that address plus 1. But the thing to note here is that we've just constructed some random address. The chances that this is actually a valid address are small because we didn't get this by taking taking the address of something that we actually have. We literally just put in a constant and said, go find me the value at this random spot. So this is probably actually going to segfault. We don't know. If it does something, if it actually returns you something, you have no idea what's there. So it's undefined in any case. So what we got, these first two, yep, we got them right. 1, 2, 3, 4, 1, 2, 3, 8, because we just added size of a pointer. This one is going to give you something that's 8 bytes higher. That should be just 1 plus. That shouldn't be 8. That should be 1 because we get an int back and then we add 1 to it. This is just something that's like some address in the stack. Who knows where that is? And then this guy is undefined, but it's probably going to segfault because it's unlikely that 1, 2, 3, 4, 1, 2, 3, 0 is actually a memory location that we're allowed to use in our program. So does everyone sort of understand those guys? Yes? Yeah, so address of the point, address of the pointer, no, it's right, okay, it is right, yeah. Yes, an int star, okay, yeah, so plus 8 gives us 8 bytes above it, yeah. So that is right, okay. So everyone see these? How we get them? These two are tricky, but these are the sort of thing where you forget what you're doing and you accidentally put in an ampersand or a star where you don't mean to, and then your program is off doing some crazy random stuff and you have no idea why. This sort of stuff can happen when you're doing pointer arithmetic. So you should be able to read through them and see that that's wrong. So pointer dereferencing, so you can dereference anything that has a pointer type. When you can't dereference an expression of type void, again, what should it give back? How many bytes at that address should it give back? Who knows? And then dereferencing a t pointer will give you a value that has type t. So if you dereference an int pointer, you get an int. If you dereference an int pointer pointer, you get back an int pointer. So it just peels one pointer off of the type, and that's what it gives you back. Yeah?
You cast an int pointer that stores an integer value
Mm-hmm.
to a character pointer.
Yep.
And then dereference it. What will you get?
You get back a character.
But you don't know what it is. Right?
So we're actually going to have an example of that. It's an interesting example, and we're gonna do that just right here. Okay, so the question was, if we cast an int pointer to a character pointer and then dereference it, what happens? Or in this case, yeah, that's exactly what we did. Okay, and then we cast it back to an int here. But so what happens? So we've malloced a integer, and we've set the value at it to be 0x dead beef. And okay, so then what is val1 equal to? Marker's kind of bad. What's val1 going to be equal to? 0x dead beef. Okay, so that one's pretty straightforward. Is there a better marker here? Okay, so that's pretty straightforward. We set the value and then we got it back. Nothing changed. That's unsurprising. But this was the question here. Exactly the question that was asked before we even saw this slide is what happens if we cast it to a character pointer and then dereference it? What are we going to get back? So we know that we get back 1 byte at that address when we dereference a character pointer. So casting to character pointer does not change the value of the pointer. We're taking the same pointer and we're asking for just 1 byte at that address. So what's going to happen? And then we're going to cast it to an int. So let's start with this part. Let's start with just the inside here, up to the dereference before we cast it int. What is this dereference going to give back to us? Yeah. EF. Okay. So why is it EF? Little endian, yeah, you caught the, you're too smart. You got it before anyone even said DE. So you might think at first, well, we're going to get back the first byte, which is DE. But remember that these numbers are stored little endian. So that means that the first byte at that address is the EF, and then the BE, and then the AD, and then the DE. So at this address is the byte EF, okay? So we have the byte EF, and now we're going to cast it to an integer. So this is a cast from a character to an integer. We're going up to a bigger type. What's going to happen to it? So yeah, so it sign extends because these are signed, a signed character being cast to a signed integer. So okay, what's the most significant bit of the hex digit E? 1. Okay, so we're sign extending with 1s then. So then we get a bunch of Fs. So the result we're going to get back is FF, 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 EF. We can see that here, that is what happened. So this is a bit strange. It almost isn't what you would expect to happen. It's sort of like you got all of these Fs that didn't exist, and then this guy that seemed like he was at the end, not the beginning. But the reason you get the EF back is because it's little endian, and then you sign extend. Is how you get all of those Fs there. So sort of you can get some interesting stuff when you're going between the sizes. So you have to be careful because you can get very confused about the results you're getting if you mistakenly cast something to a different size than it actually is and then dereference it. Okay, so any questions about dereferencing pointers? Okay, so Malloc. So the basics of Malloc, you're writing a Malloc implementation. So you've all used Malloc in your other labs. Malloc allows you to get memory allocated, and then when you're done with it, you call free. so that you can get it back again the next time you call malloc. So sort of the different things you need to know, some different terms. Malloc, of course, is the function that actually allocates memory for you. Calloc is the same as malloc, except you're guaranteed that it's going to come back all zeros. So essentially you can think of that one as it mallocs and then it writes zeros to all of it before it gives it back to you. And then realloc. So realloc is a special function. What it does is, say you have some memory that you've been using and all of a sudden you realize that it needs to be bigger. I don't know, maybe you're doing some sort of resizable list implementation or something like that. And you realize that you need to make it bigger. What you can do is you can call realloc and it will give you back a bigger chunk of memory, or you can actually, I think you can make it smaller too with realloc. Yeah, you can get back a different size chunk of memory, but without ruining the contents of what's already there. So malloc is the one that's more difficult to implement. Calloc and realloc are actually just going to be small wrappers around malloc. Don't think that you need to implement something completely novel and different for those two. It's just malloc with a little bit of extra work to clean up and do whatever the extra stuff is. Then there's free. So free is the function that once you're done with some memory, you give back the pointer that malloc gave you, and then free lets the malloc implementation know that it can allocate that memory for you again in the future. Malloc and free are the big two functions you'll be writing. Then there's the function sbreak. So in terms of actually getting this memory to use, you'll be using a function called sbreak. And sbreak changes the bounds of the heap. So you can use sbreak. You can read in the book or in the man page for it for the exact details. But what sbreak will do is it'll let you increase the amount of memory on the heap as a whole that you can then give back to the user. So eventually, you might run out of memory to be allocated. You call sbreak to get more when you need it. Payload. So each block in your implementation has a payload associated with it. The payload is the actual stuff that the user is writing to. And then there's fragmentation. We've got some more slides on that, so we'll get to that in just a bit. And coalescing. So sort of the idea of if a user allocates a block here, and then they allocate a block right next to it, and then they free both of them, well then it would be nice to say, okay, what we have in our data structure is one really big free block, rather than keeping it as two small free blocks, because if someone asks for this much memory, we can give it to them as this block here. And so there's sort of a couple different ways you can do coalescing. Sort of you want coalescing, you want things to be able to look on either side of them to know if they can coalesce. And also you need to think about, well, when do you want to do coalescing? Do you want to do it all the time right away? Or do you sort of want to wait to coalesce? Like all the time right away when you free, you coalesce if you can, or do you wait until someone tries to allocate memory and then you check and you coalesce, if you need to? That's a design decision you get to make. So here's an example of some allocation. So we start with allocating 4 bytes. So the allocator fills up those 4 bytes. As those are marked as used by this first allocation. And it's keeping track of them that they're associated with this pointer 1. This is sort of the data structure you have to write, is going to have to keep track of which pointers are associated with how much memory. And then we allocate 5 more bytes, so we just give back the next 5 bytes. It's easy enough. Then we allocate 6 more, so we give back the next 6. And then when a call comes into free of P2, we need to know that those 5 bytes in the middle were the 5 that we're allowed to free. So now those get marked as free. And then someone's going to come and malloc 2 more bytes. We can give them the first 2 bytes of that chunk of 5 because they're free now. We're allowed to use them for whatever we want. So does that sort of make sense? This pattern of we've kept track of which bytes are associated with which pointer, and we can fill in these bytes with these different blocks. And sort of now you'll sort of see, we've told you since the beginning of the class the contents of the memory when you malloc it are undefined. You have no idea what they are. Now you can see why that's the case. Is because what you're really getting back is potentially something that you freed previously in the program. So in that case, whatever you wrote to it back then is what's in it now. And so you might notice a lot of the time when you malloc memory, it's already filled with zeros. Well, then it's probably the case that it's something new that hasn't been allocated before. But in the case that you get back something that's overlapping with a block you had previously, it still has whatever was in it before. It never gets cleared out because that'd be really slow. Okay. So that's that. Okay, fragmentation. So I said there was two types of fragmentations, internal and external. So sort of there's a minimum block size that we can support. So our data structure is going to constrain how small these blocks are allowed to be because we need to be able to store a certain amount of information on them. So if someone is just allocating 1 byte, and our data structure doesn't have a way of handling blocks that are just 1 byte, then we have to allocate more than 1 byte even though the user is only getting 1 byte back is what they're expecting. And that's called internal fragmentation. So that means we've had to reserve some number of bytes that are essentially wasted. Everything has to be aligned to 8 bytes. Constraints like that, if you just keep allocating 1 byte over and over and over, we're going to have issues with 7 bytes being wasted every time, potentially, is what we likely see. So that's internal fragmentation. And depending on how you design your data structure, you can reduce that. Certainly, you don't want your data structure to require a minimum block size of like 1,000 bytes, because then any allocation smaller than 1,000 bytes is going to have a lot of fragmentation. Then there's external fragmentation. So external fragmentation happens when there is free space in our heap, but there's not a single free block that can handle the allocation we want. So in this case, we allocated 4, 5, and then 6, and then we freed the 5. And now we're asking for 6. And we've got 7 bytes free in our heap total, but we don't have a block of size 7. We've got it split up into 2 blocks, one of size 5 and one of size 2. So the only thing we can do is actually increase the size of our heap. We need at least 5 more bytes at the end of it to be able to allocate a block, a continuous block of size 7. So this is external fragmentation because theoretically, if we had sort of ordered these things differently, we could have fit it all in without allocating more space. But in the order that we actually did it, we did have to allocate more space. So this is sort of something that you don't know what the pattern of requests is going to be. You have to sort of just guess at what will be best, even though you don't know what's going to happen in the future. Because you have to give back that pointer right away. You can't sort of wait for the guy to call Malloc 5 times and then you give him back 5 pointers, because he might want to use some of them. That'd be really annoying as a programmer. So, so the thing is, you'll probably, you won't be able to always avoid external fragmentation. But by picking different heuristics in terms of how you pick the free blocks and how you allocate the memory, you can come up with something that on actual traces maybe performs well and minimizes the amount of external fragmentation. So that's something to play with, is different heuristics. That would be things like next fit versus best fit in terms of picking your blocks that you're going to use. Okay, so implementation hurdles. So these are sort of some questions you should ask yourself and understand. You should be able to answer these questions before you just start writing code, because if you just start writing code and you don't have a clear idea of what these are going to be, you're going to get stuck or confused. So how do you know where the blocks are? This is sort of something, you need some data structure that keeps track of where your blocks are, where your free blocks are, where your you don't need to necessarily keep track of the allocated blocks as long as you know how big they are, right? Because you're going to get back the pointer for them in the end. But you do need to know how big every block is. How do you know which blocks are free? You have to be able to do this all in real time. You can't sort of wait to do it. Free takes just the pointer, so when you get back the pointer, you need to somehow know what size it was. And you're not allowed to have a global data structure storing this. So you have to somehow, local to that pointer, be keeping somewhere that size. And so sort of the idea, we give you is that you give them back this pointer here, and then, sort of there's some memory right in front of it that keeps information about the block there, like the size. And so then anytime you get back a pointer from free, you just sort of go back that number of bytes and read off what the size is there. That's also how C0 deals with keeping track of the size of lists. If you've taken 122, it just sort of tags the memory in front of the list with the size of it. That way it can do the runtime checks that C doesn't do. Let's see. Okay. So we need a data structure that does this. And of course, we can't just allocate memory with Malloc, because that's what we're writing. So we need to be able to actually directly manipulate the bytes on the heap in a way that keeps track of this information for us. So data structure needs to tell us how big the blocks are, where they are, which ones are free. We need to be able to change it. We need to be able to find the next free block. We need to be able to mark blocks as free or allocated. And we need to be able to know when we're out of blocks and be able to handle, getting more memory if we don't have enough blocks to do an allocation that's requested. So this is all sort of is a simple implementation of this and a couple different strategies described in the book. We don't get a data structure. We just get pointers. So you'll be sort of keeping track with all of your blocks that you're actually using allocated. You can just keep some of the bytes in front or behind or both of that block of memory with data in them about it. Information about where the other guys are, how big I am, if I'm free, if I'm allocated, that sort of stuff. And so you can read the book and see some different decisions you can make and think about which ones you want to do. I'd recommend starting with simpler things. So we've sort of divided into 3 categories: implicit lists, explicit lists, segregated lists. I recommend starting with the simpler ones and then iterating up to the bigger ones. If you just start to try to go to the best one immediately, you'll probably make a big mess out of everything. If you factor it well, upgrading one to the next is not hard. So implicit list, explicit list, these are all in the book. I want to get to a quick demo. So I'll just skip through those. Heap checkers. So part of the assignment is writing a heap checker that checks different invariants of your heap that should hold. So this is here to help you, and you should write it as you go. Some people think of it as something to just slap on at the end after they finish, but it's actually going to make debugging a whole lot easier if you have a good heap checker. So writing it as you go will actually help you a lot and save you some time. So what the heap checker does is you just should encode all of the invariants in your heap. You should have a check for all of the invariants of your heap in this heap checker, and it should run silently as long as they all hold. So you'll just insert calls to this heap checker in different places throughout your code every time you're manipulating it. And you want to make sure that it was maintained. And as long as everything's good, it shouldn't say anything. Otherwise, you'll get a ton of output. If you want to add a verbose flag, maybe you can do that. If you're actually running into issues and you want to be able to turn on some more output, you should consider using a macro to turn the heap checker on and off. I'll show you how to do that in just a moment. And then there's this built-in macro called line. That will be useful. I'll show you how to use that in just a moment. But this heap checker is really useful, and it'll help you debug. So let me show you real quick a couple things. So you'll download the handout on tar. You get a bunch of stuff. This is pretty normal. You make it with make, just like before. And so the file you're actually editing is one called mm.c. And I've replaced it with the implementation from the book to show you different things you can do. Why is it frozen? Okay, so some different things. So the heap checker. So here we have the heap checker. And what I've put inside it, so you don't normally want this because this is going to give you a lot of output, but it takes an argument line number, and I'm just going to print out that line number so you can see it working. So sort of what you can do, so if we go to the implementation of free, maybe, see if we can find it. Here it is. Okay, so say we want to run our heap checker every time after we call free to make sure that everything worked. So then we do mm heap check, and then we do this macro underscore underscore line in all caps underscore underscore. And what that's going to do is it's a preprocessor directive that, it's a special macro that gets replaced with the line number before it actually runs. And so depending on which line you write this on, it has a different value for every line. And so then we'll be able to print out the line number of the heap check call. And this will be useful when we're debugging. If we want to see which heap check failed, we can print out the line number of it. Then maybe we'll do the same thing in Malloc up here. We'll do mm heap check underscore underscore line underscore underscore, and we got that. Okay, so now we've got that. We can make. Oh, it's check heap, yeah. Check heap. Check heap. Okay. So we build it. So the way you run a trace, we've got this M driver, similar to before. You can run it on all the traces, but I'm just going to run it on one. So you can run it on one with -f. That's useful when you're debugging. And then you give it the name of the trace. So they're all in a folder called traces. And then, we've got these different ones. So let's run it on short one, because that's probably not going to take too long to run. So then what does it do? Okay, so now we see all of this debugging output. So this is sort of why you don't want to have your heap checker printing when everything's okay. Because imagine a trace that's 1,000 times longer than this, and we actually print out more than one line each. You're going to get way more than is ever useful to you. But we can see here that we've called it from two different lines, 147 and 127. That's the line for free and the line for Malloc. And then we see here at the end, we have a certain util. We had a util of 66% and a throughput of 1,015,000 ops per second. And that's enough to give us 15 out of 100, which is going to get rounded down to 0 because there's a rounding down thing that happens if you don't meet a certain threshold, so that you can't just submit the book implementation and get points for it. But don't worry, if you actually spend time on it, it's not hard to get above that threshold as long as you're designing everything well. Okay, so let's see. So yeah, that's how you use the line. It's just the __ line. Another thing that's useful to be able to do is then turn that heap checker off, but not have to remove all of the calls to it. So what I'm going to do is I'm actually going to rename the calls to heap checker just check heap rather than check heap. See if I can find the other one. Okay. And then what I'm going to do is I'm going to write a macro up at the top of the file. And I'm going to say define check heap of line number to be check heap of line number. And this is going to do the same thing that we did before. So if we make, I actually already have it up here. Never mind. Okay, so I have it up here that I'm defining check heap of line number to be check heap of line number. So now it does the same thing that it was doing before, where we run it. Why is it not happy? So now it will do the same thing as before. We run it. It prints out all this stuff. But now we want to turn off the heap checker. What do? We just redefine check heap to be nothing. And then all of the calls to it get replaced with nothing. So then it doesn't actually run. And so now we make again, we run it, we don't get any of that output. And since your heap checker is probably going to be quite a bit slower than a lot of the stuff that it's happening around, because the heap checker has to go through the whole heap, and maybe you've only done a constant time update, and then you call the heap checker. It's going to slow down things a lot. So in terms of actually knowing what your performance is, running it's going to make it a lot harder to tell. So you can see that the throughput went up by quite a bit. It went from 3 to 30, and now we actually have a 42 out of 100 just by turning off that printing was enough to slow it down. So having a macro like that is good, because then you don't have to change every single use of heap checker every time you want to turn it off or on. It's much quicker. And then one last thing real quick is profiling. So you might find it useful as you're going. You might want to know sort of where it's slow, or what's happening if it's not as fast as you expect. In the make file, if you update the flag from -G to -PG, it'll generate profiling information. And so then what you do is when you make again, and when you run it, it'll actually generate profiling information with it. This actually slows it down, so we see our score went down again, so you'll want to take that out, of course, to know how fast you actually are. But what we can do is it's created a file called gmon.out. That's how we know it ran. And if we run this program called gprof, and you can read the man page for it to get all the details, but if we run gprof on mdriver, then, well, it puts out a lot, so let's put it through less. Then we get this great information that says we called free 60 times, malloc 60 times, coalesce 20 times, init 10 times. And then here's how many seconds each one took. It turns out that this trace is short enough that starting the whole thing up is actually longer than running the trace. But we can see if we had a longer trace, we'd be able to see, how much time is it spending, relative time is it spending in all of the different parts. We can sort of pinpoint what's slow. Is there something that we called way more than we expected to be calling? And this is useful in terms of, once you've got something that works, but it's just, you just want to make it faster, and you want to know sort of which points would be most useful to update, where should you look to get that best improvement in speed. Profiling it will give you that sort of information. And then, to actually make sure you take out the profiling flag then if you actually want to know how fast it's going, because generating the profiling information does make it go slower. So you can take it out and make again and run some more. Okay, any questions about heap checker, profiling information, that stuff? Yeah?
How is it, so it was continuously printing, how would you make it run like only when it detects an error?
Right, so you'd have something, you just have all of any printing that happens in the heap checker would just be guarded by, like, if it's good, don't print, else print. Yeah. Other questions? You guys can go.